size, the delay almost remains constant because we are writing simultaneously to all the memory strings. Similarly, if you take about the energy, write energy, the write energy is matching almost with the previous method, but it's all right because we are actually compensating with the delay. And then when you see the PDP, EDP, energy product with the delay, then the presented method is doing much better. Okay. Similarly, when you go for a read, you can see very interestingly here the read delay is very, very low, even when you increase the array size, which means that it is independent of the array size. You can have a very low or constant read time, which is a great advantage with our new method. Then what we actually analyzed is, we took different memory strings sizes, the array size, from 2 by 2 to 8 by 8, okay? And then we performed across different methods. So this is our improved LUT, the second LUT. This is our first LUT, first model, and the previous works. So what happens is, if you keep the write one operation, the number of affected memory strings is almost 0 in all the array sizes. Okay? Whereas our previous method is actually increases the number of memory strings affected. And the worst is actually with the previous methods, like, you know, also they affect the memory strings. So in terms of NSP, you can see that our improved method is not at all affecting the NSP. Whereas the previous methods, they cross from 0 to 0.8, which means that you are crossing and corrupting the data. Okay? So that's with this write one. Write 0 is similarly, you can see that our improved LUT is not at all affected, and you can see that it is in the 1 means the improved LUT remains at 1, whereas the previous methods that goes to 0, which means that your data is again corrupted whether you write a 1 or a 0. So we did another experiment for the read performance. For example, when you increase your array size, you want to see what's the difference between 0 and 1. Okay? If the voltage difference is very small, then it is very difficult to read between the 0 and 1. And we did this performance, and we found that the difference in the output voltage remains almost like, you know, 0.7 to 0.8, very close to 0.7, which is very, very interesting result because we can differentiate between 0 and 1 very easily with our method. We took a real FPGA, which is, Vertex 4 FPGA and then Vertex 5 FPGA. In both FPGAs, we implemented a lot of benchmark circuits. You can see the number of LUTs in these benchmark circuits. Okay, these benchmark circuits are there, and we implemented using our method, okay, of designing non-volatile and also using SRAM. Interestingly, you can see here the Vertex 4 FPGA. This is a delay, right? The SRAM delay is very, very small. The SRAM delay is very small when compared to the improved LUT. It is the same case with Vertex 5 also. We can see that the improved LUT has got a larger delay when compared to the SRAM because we are moving the ions here, and writing into SRAM is much faster. So moment when you see this result, the complete result, complete your experiment is gone, because you already, you know, you are not successful here, right? Okay, what we did is, our argument is, now let us look at the read operation. When we look at the read operation, the improved LUT is performing much better when compared to the SRAM. Okay, so what we did is, we did an experiment. So here it shows that KT is the number of times you write or read a cycle. You write once and then you read number of times. Usually FPGA is something like you write once and then you read many times. That's a FPGA device, right? So we don't actually write often. We program as a configuration and we try to actually read many times. So using that concept in the mind, so we actually performed between the Vertex 4 and Vertex 5. We found that, okay, after first write, you wait for nearly 650 to 700 cycles of read cycles, okay, and then you match the delay matches. After that, after anything above like 700 cycles, the read is going to be advantage to you. Do you understand this concept? The previous, the concept what I'm explaining here is, the write delay is very much with our proposed method, but the read delay is very small. So how are we actually compensating this is, Yeah, when you actually write anything above like 700 cycles, or when you read 700 cycles after one write, then your advantage starts, right? So how long it's going to take, that's the time that is given here. You can see from very small nanoseconds to 10,000 nanoseconds. Within 10,000 nanoseconds, you reap the benefit of the circuit. Okay, and this work is also been published in Integration Real Essay Journal. And if you want to know, so each one is actually a paper. Okay, I'm just putting some, very highlights of the paper alone. So you can refer to this paper. Now we have designed the LUTs, right? So I told you that the LUTs can be replaced in an FPGA. Also, the LUTs can be used in the new computing paradigms. So I hope that you learned about near memory computing, in-memory computing. Have you heard of these things? So actually when we move the data transfer, right, from the CPU and fetch the data from the memory, there is a bottleneck now, because the CPU is doing much faster process, and you need to transfer the data through the copper wire and get the data. So there's a bottleneck because of this copper wire. So what people are trying to do is, they're trying to bring the memory very close to the CPU, so that to avoid the delay and then increase the performance. But still, it's not the in-memory computing, near-memory computing, there are chips available in the market by Samsung and HP and all. And people are not content with that. People want to do in-memory computing. In-memory computing means, in the memory itself you do some computing. Okay? So this is still actually growing area. If you are interested in doing some research or some final year work, you can think about it, in-memory computing. So in the in-memory computing, there are memory devices. That memory devices is not completely going to offload your CPU work. It's going to take some of the load and then give it to the memory. For instance, like multiplication. Multiplication is quite commonly used in all applications, right? Image processing, DCT, you take anything. Multiplication is a basic thing, right? So you need to do a multiplication. So the multiplication operation, you can actually throw it into the memory. So there, we can actually use this LUT. How we can use the multiplication? You know about multiplication, right? We need a lot of circuits and then full adders, half adders to perform. Here it's very simple. You take the multiplier, you want to have 2 bit by 2 bit multiplication, right? This is like a 4 address lines. I'm just taking as a 4 address lines. So I'm putting the 4 address lines. And the multiplied value is in the memory. So that's all, very simple. So whenever you want to do multiplication, you take the multiplier and multiplicand, make a bit, go and read the data, you get your multiplied result. So if you can do this inside the in-memory computing, then it's wonderful. Okay, so this is one of the application. And most importantly, the delay through the LUT is constant. I want to touch a little bit on the sequential logic. The sequential logic we introduced, you know about this is this so-called as your D flip-flop, right? We introduced the memory, memristor here. When we introduce the memristor, you can see that that this is a G and this is a DM, and you can see this is a VDD. Okay, the VDD, there is a small power disturbance happening to this VDD. When there is a power disturbance happening in VDD, you will see the data will be lost. But we are using a memristor here, so what happens with this memristor is the data actually comes back. Okay, so this is with non-volatile memory. You can see that the data here actually is coming back after the power disturbance. Whereas in the normal case, the data will not be coming back, it will be going to the 0. So by using this kind of memory in the DRAM or D flip-flop, you should be able to retain the data, even there is a power disturbance. An application for this I can say is in space. There are a lot of radiations are there, and during this radiation, when you subject anything to the electronic devices, they can actually change the state of the memory state of the electronic devices. Not only in space, even the nuclear plant, like places like CERN where they are testing, the electronic devices, they are all actually susceptible to these kind of devices. What they do is, they use one-time programmable device. So you program it once, that's it, you cannot reprogram it. But here, if you incorporate the memory inside, like non-volatile memory, it's possible for you to reprogram it. That's the concept that we would like to actually bring in here. So if you combine this with the LUT, then you get your so-called as configurable logic block. Once you get the configurable logic block, then whatever that you program will be there and it will not get destroyed due to the power supply. Okay. So I was telling you about the sneak path current, right? There are several methods people are actually adapting to resolve the sneak path current, because we resolve the sneak path current that's used only for the LUT purpose, right? But if you want to create a big array size, and there are several methods. The writing scheme is ours one. And one diode, one resistance method is there. One transistor, one resistive RAM, one selector, one resistive RAM, and CRS. These are the methods the researchers across the world are working. I'm just going to touch only one here. One selector, one resistive RAM. Initially we had only one resistive RAM, that memristor, in between the two metal layers, right? Now what are we trying to do is, we are putting a selector device there. So the selector device goes in series with the memristor. So in each cross section there will be a selector device and a memristor. What the selector device is going to do? It is going to stop the sneak path current. Sneak path current will be there, but the sneak path current will not enter into the memristance. So how does this work? For example, the selector, you can see this is a selector device, okay? And the characteristics of the selector device is something like this, right? The voltage current characteristics. The resistive RAM initially was like this, you can see in the dotted line. After you implement 1S 1R, what happens is, from minus 1 volt to positive 1 volt, you can see there is no change in the resistance level. Okay? After that only the resistance actually switches. So we are actually increasing the voltage range. So if the voltage actually falls between 1 and minus 1, and it is not going to affect your memristance. Okay? So that's one of the method, whereby we can use selector and resistive RAM. Currently we are working on something new. Okay, we have published it, which therefore I can't actually tell it here. So we are actually coming out with a new method to actually replace this selector with another method. We have fabricated this one selector and also using memristors, okay, and we fabricated using these devices, and we finally got our device, this memristance, that what you see here, okay. So this memristor has a selector device which is like platinum, titanium, tantalum oxide, TaOX, TaO2 and platinum oxide. So platinum device, its characteristics is shown here, and we also modeled it, okay, using tunneling junction. And we actually integrated the selector with the resistive RAM, and you can see the entire structure. This is selector and this is your resistive RAM. And it gives you a perfect result, whereby this is your memristor, this is your resistive RAM, and here what you see is your so-called a selector model, and combination of these two gives you a new memristance device, something like this, whereby the switching voltage is actually from minus 1 to plus 1 voltage. So you can see that whatever we exposed previously, we actually did it physically, physical device we fabricated, and this is our result, Apart from the resistive RAM, there's another area that is emerging, whereby we can actually store multiple, bits in a single device. Okay, so in a single device, whatever that I'm showing you, memristance is like in 5 nanometers. But to store a single bit in a SRAM, we need 6 transistors. So the footprint is very much reduced. But now, with a single device, you can store multiple bits. That's quite interesting. How it is possible? You can have multiple resistance like this. When you are switching from a high resistance, low resistance to a high resistance, there are multiple resistance regions are coming in. So this multiple resistance region, if you capture that and use it, you can actually use it for a different logic levels. Okay, but the problem is, they are very, very close, right? So jumping from one resistance level to the next resistance level is very easy. So we must know that we must know to distinguish the in-between resistant levels. Okay? Distinguishing from here to here is easy. But in between we have multiple resistance levels, so distinguish that is becoming a very challenging one. But if you could distinguish, then there's a great potential. What's the great potential? I can actually show you here one example. Like this in a half adder, right? So to implement this half adder, we have like 4 memristors. So this memristors has got like 4 resistance levels, 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so I am programming this to 0, 0, programming this to 1, 0, this one to 1, 0 and this one to 0, 1. So out of these 4 resistance level, we can program each memristor to one of the resistance levels. So we programmed in such a way that it is 0, 0, 1, 0, 1, 0 and 0, 1. Okay, now you are going to read the data. So AB, this is, if you want to read the data from here, you will be getting an output resistance level of 0, 0. If you read it from here, you will be getting an output resistance level of 0, 1, 0. Similarly, if you read it here, 1, 0, and if you read it from here, 0, 1. Which means that this complete circuit, that you could be able to get it through only 4 memristors with 2 outputs. Okay, it's possible because of the multiple resistance levels. Okay. There's another issue that, with the memristors, that when you keep on using the memristors for a quite long time after several cycles, you can see that the high resistance actually slowly reduces, and therefore it decreases between the R on and R off. Here the R on and R off is very good, but slowly it decreases. At one point it actually merges. This is another issue, open issue, where we need to think about in terms of materials. There are several materials people are actually using it, not only restricted to what I'm actually showing it. There are a lot of research going on, a lot of materials they are using it, and one of the interesting area where they are using it is neuromorphic computing. Okay, you know about the neuromorphic computing, right? The neuromorphic computing is the computing that is going to use spikes. Can you imagine a CPU without running with a clock? We need a clock signal, right, to run. So Intel has released like 2 processors, Logi and Pohi. This Logi and Pohi, they don't use any clocks. They use all, spikes. Okay, which is going to be completely asynchronous. If we have to move to that direction because we are in a big data world, so we have to move into that direction. So when that comes into picture, and many people are actually using memristors to actually design neuromorphic computings. Okay. Right. This work is also published in IEEE Design Automation Test Europe. It's one of the important conferences, and it's selected as one of the best papers there. And there are a lot of opportunities to replace the flash, it's a very good opportunity for using memristors. I'm not only talking about the memristors, the other, memory devices. We are actually somewhere here, We have a lot of things to do to replace the solid state disk, DRAM, universal memory, neuromorphic computing. Okay, a lot of things are there. We are left with a lot of opportunities. That's what I want to say. In conclusion, we learned a need for fast access and large storage is inevitable. Emerging memory technology is a potential candidate for that. Okay, filled with a lot of challenges and opportunities, and leaving us with a great time. And these are our publications, particularly related to these memristors and LUTs. These are the list of publications. And this is a team of us, and these are my PhD students, who some of them graduated and some of them are actually going through still. And I'm collaborating with Professor Lombardi from Northeastern University and Professor Kaushik from IIT. Also, they are very much involved in this. So apart from this, my core areas are like approximate computing, FPGA, fault detection, and neuromorphic computing also, right? And this is my campus. And if you have time and if you visit Malaysia, I would like to actually welcome you to my campus, a very beautiful campus. We can go around the lake and take you around the campus, right? Thank you. I stop here. Okay, thank you for listening. If there's any questions, I can answer you.
Session. Any queries?
Don't worry about asking questions. Any question you can ask me.
Actually, I want to ask about the MTech. Wish to do an MTech at your campus.
Actually, our campus, we have a master's program, but what I suggest you is if you want to do master's, you can actually go to Nottingham campus in UK. Okay, that's better options are there when compared to this. For bachelor degree, yes, or for PhD, if you're looking for, definitely it's possible to do a PhD.
Thank you.
Yes. That's power dissipation. If you can see, we are actually moving the ions. Therefore, the power dissipation is on a higher side when compared to the SRAM. But when we weigh the so-called as the benefits over the disadvantages like SRAM, the area is very big, 6 transistors. And here the area is like 5 nanometers. And this can be placed in the metal layers, whereas SRAM need to be done in the silicon itself. So we don't need to touch the silicon. We can just put it in the metal layers. So that's another advantage of this. And most importantly, SRAM is volatile. And it is highly susceptible to any radiation environment, or it is also susceptible to power fluctuations. Whereas here, we can store the data. Right now, what people are doing in FPGA is they are using a flash memory to store the configuration bits. Once the data is corrupted, we need to offload these configuration bits, which is on the flash, into the FPGA itself. So, which means the system need to be down for some time, just before we are doing this data configuration. So, here, in case, if these kind of FPGAs are coming into the place, then we are not going to affect by the power dissipation or power disturbance. And then the area is going to be small, and the read and write time is the matter now. The energy, of course, there is a cost that we pay, but what we actually reap the benefit is the read and write time and the area, and of course non-volatility. Any other questions from this side? One question? Last question? Yeah.
Is there any environmental impacts for this one? Because there it is using titanium oxide and those kind of things. So it is basically not that environmental friendly, right?
Even though I'm talking about technology, when you talk about like a human being, any technology is going to affect the environment, okay? But there's a need for us, right? So here what I'm showing you is titanium oxide is one of the material. As I told you, there are like a few hundred materials people are actually working on, where we are not actually exposing to all the materials here. My main idea is here to expose you what people are doing it and what it is all about, and give some examples. But when you see there are other materials also people are actually using it. Definitely any technology for personally what I feel is disturbance to nature. Please. It's not storing the power. For instance, what happens is you are moving the electrons, you are moving the ions, right? That means the entire atomic structure, right? And then you're retaining there. When you remove the power, it remains there. That's it. For example, the normal current, the electrons are moving. The moment you actually stop, the electrons flow is stopped. But here, you are actually changing the movement of ions. So therefore, what happens is, it remains there. As long as there's no power, it remains there. Unlike your NAND flash actually uses a transistor, right? Yeah. So here it's smaller in size and it uses, and that's why, as Professor actually just now asked, it requires some more energy. All right. Thank you for asking the question. Any last question from that corner? You all happy? Say happy or no? Happy. Okay.
Now I invite Ms. Aishwarya, student representative, to deliver the vote of thanks.
Good afternoon, one and all present here. I take this opportunity to propose a vote of thanks on behalf of our whole family of PSAT for this informative talk session under SpecCon conducted by the Electrical and Electronics Department, PSAT. I would like to thank our speaker, Dr. T. Nandakumar, who is a senior member IEEE, fellow HA UK, and MIET Professor of Electronics, Department of Electrical and Electronics Engineering, University of Nottingham, Malaysia, for not only sparing his valuable time for us to grace this occasion, but also for enlightening us with his commendable talk on the topic of resistive RAM-based non-volatile logic design for low-power computation. Today's talk was full of knowledge and it gave deep insight into the topics emerging non-volatile NV memory technologies, switching mechanism, and electrical modeling of NV memories, non-volatile FPGA, and more. Sir, your presence and expertise have truly enriched us and we are deeply grateful for your contribution. Thank you so much.
Thank you very much.
I also extend my appreciation to our diligent volunteers and all the participants whose active engagement made this session both vibrant and successful. Thank you all for your invaluable contributions. Thank you.
Thank you, Aishwarya. As a token of our love and gratitude, we would like to present a memento to our person Nandakumar. Rajivan sir, please do the honor. Please do the honors. Memento. Thank you, Professors. With this, we wind up our offline sessions today. Thank you all for being here. All participants kindly join for keynote session, which is conducting in online mode in IEDC room. Thank you.